So let's talk about the theory of a capacitor. Hopefully we'll get to see it working this afternoon. So if one is going to charge a capacitor, well, we need to draw a capacitor. And in the book, they don't start drawing circuit diagrams yet because we haven't started circuits, but we're going to start them tonight. So we're just going to start drawing circuit diagrams right now. Okay. So a little lesson on circuit diagrams if you don't know anything about them from before. When you're drawing a circuit diagram, a wire is just a straight line. And in real life, wires bend, right? And they bend in little curvy waves and whatever. In a circuit diagram, wires bend at right angles. Yes, they do, because it makes it prettier. Okay? So I just want you to be familiar with that, not freak out about that. That's what you should expect. That's what you should draw as well. Okay? When you're drawing a capacitor in a circuit diagram, it is a little representation of exactly what a capacitor is. It's two parallel plates. So when you draw it, they're going to be hooked to wires. And it just looks like that. Two lines that are the same length, okay? And they're hooked to wires. That's it. So you can have them going horizontally or vertically. It doesn't matter. But that's what a capacitor will look like. And the other thing that we're going to need right now is some sort of EMF. And since our generator doesn't work, I know, right? We're going to go ahead and get some batteries and use a battery, okay? So a battery, or sometimes they call them cells, and we'll talk about the difference between that later, is drawn very similar to a capacitor, but instead of having two lines that are the same length, they have two lines of different lengths, and the different lengths represent the two different potentials, okay? High potential, the positive is on the long side, and the short end is on the negative side. So those are the three pieces that we're going to need right now. We'll add some more stuff next time, or when we're in lab, and we'll talk about that. So when we're going to build a circuit diagram to talk about charging a capacitor, oops, you don't need to look at pictures of, here I am. There we go. So we're going to take a battery, and hook it up to a capacitor. There you go. I'm going to go ahead, I'm actually going to change this wire on top here, and I'm going to put a switch in. What does a switch do? It opens and closes the circuit, right? So nothing's happening right now. There is no potential, there's a little potential difference here, but not over here. As soon as I close that switch, what happens? Let's talk about it physically. What happens?
Difference happens at the capacitor.
Right. So a potential difference is established across the entire, across the entire thing. So physically, let's think about this. Actually, literally, what's going on, and this is something I'm going to push you to think about over and over and over because it's really important. As soon as that switch is now closed, so I closed it. Now the potential difference that exists there, the separation of charges that happened due to that chemical reaction in the battery, has now caused a potential difference across that entire wire. If there's a potential difference, that means that we can say that inside the wire there is an electric field. Are you with me there? Okay? The electric field, which way is the electric field going to point inside the wire up there? If we were going to zoom in on a little piece of wire right there. Is it going to go to the right or the left in that little piece of tube? To the right. Why?
Because positive charges move towards
the negative terminal. Does that make sense? Okay. Now, later this afternoon, after we've read the stuff in the book, if you haven't read it yet, we're going to get things to flow all the way around. But the beauty of a capacitor, are there going to be charges that are going to flow in between those two parallel plates? No. It's a big deal, okay? Big deal. A capacitor that is working as a capacitor, okay, does not allow charges to cross between plates, we'll say. The whole point of a capacitor is to collect a bunch of charge up here and to collect a bunch of charge down there so that you establish an electric field in that space. Are you with me there? Okay, so if we zoom in on the capacitor as it's being charged, what do you have over here? A bunch of positive charge. That positive charge is there because there was an electric field pushing the positive charges around, right? So there's a bunch of positive charge here. That positive charge isn't going anywhere, but the fact that there is positive charge here does what to the positive charges that were hanging out here? They're gone, right? Which leaves us with a bunch of negative. Are you with me there? So you've got a bunch of positive up here. And a bunch of negative down there. Yes, via induction, right? It's not actually moving charges. Okay? And that causes an electric field to be created within that gap. That electric field is the one that we've been spending all the time talking about. Okay? Is that okay with everybody? In problems that we've done in the past, we've then had charges that have moved through that electric field. But when you're talking about a circuit, we don't have charges moving in this electric field. It's just an electric field that is established to store charge. Does that distinction make sense to people?
No, say that one more time.
I'm trying to. What did I just say? Okay, so the charges that are here and the charges that are here establish an electric field. They're not there to do any acceleration of charges.
Oh, yeah.
All they're doing is storing those charges there because, so here's the deal. Two things. Are positive charges going to keep flowing here forever? Are they just going to keep building up forever? And negative charge here? No. When is it going to stop?
When you can't fit any bunch of charges on the dielectric.
Blah, 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 mumble, mumble, mumble. Andrew, what?
The potential of the capacitor plus potential of the battery.
Right, when this potential here and this potential here are the same. Does that make sense? Okay? So the potentials, when they become the same, the capacitor is what we call fully charged. So fully charged capacitor, okay, means that the potential difference across the capacitor, delta V sub C, is equal to delta V of the battery. Okay. At that point, if I open the switch again, does anything happen? No. I've still got a potential difference there, right? I've still got stored charge there. And that's the purpose of a capacitor in this kind of situation. Now I can use that charge later, and we're going to talk about discharging those capacitors, why we care, but we do that next chapter. Okay? So for right now, we're just going to hold on to that idea and write down a couple more things. We know, because we've talked about this before, that delta V sub C is equal to the strength of the electric field times the distance between the plates. Right? We said that a long time ago. We also talked about last chapter, or maybe a couple chapters ago, I guess it was a couple chapters ago, that the electric field established inside a capacitor was equal to the charge on the capacitor divided by epsilon naught times the area. Do those look familiar to you? We established both of those earlier, like last chapter when we were together. we can put those two expressions together, and instead of saying E, I'm going to throw this big mess in for E, and let's see, I guess I solved it for Q first. What did I do here? Hold on, let me back up. Let's do this thing one at a time. So if we solve this guy for Q, so Q is equal to E epsilon naught times A, and then let's throw E in over here, and so E is equal to delta V over D. Is that okay? And so I'm going to throw my E in the other way, this way. We can say the charge stored on the capacitor, or stored in a capacitor when it is fully charged, is equal to epsilon naught A over D. I'm rearranging this a little bit for a good reason, times delta V sub C. The charge stored on a capacitor is dependent on two things. This first piece here, okay, has to do with the physical, parameters or the physical properties of the capacitor, how big the plates are, okay, and it's the overlapping part of the plates. So if you have one plate that's bigger than the other, it doesn't matter. It's going to be the size of the small plate. Or if you have two plates that are of the same size but they're not overlapping the entire way, are you with me there? Then it's just the overlapping part that we care about, and the distance between them, times the potential difference. This little guy right here, that piece is called the capacitance. Okay. The capacitance is measured in farads. So capacitance is marked with the letter C and has a unit of farads. Okay. Farads named for Michael Faraday, okay, who did a lot of stuff with electricity and magnetism. We will come to love him in the next few chapters. Okay. A farad is really, really big. The capacitors that are used in electronics that you use, and capacitors are used all the time in electronics that we use. Modern electronics wouldn't work without capacitors, okay? We're talking like micro or picofarads, okay? Big, like 1 farad is a lot. Kind of like a coulomb of charge is a lot of charge.
Isn't 1 farad and a 1 farad capacitor hold 1 coulomb?
Yeah, by definition. At 1 volt, right? I mean, like, yeah. But yes. Okay. The capacitance, I said this before, but I'm just going to write it down here, is dependent on the physical parameters of the capacitor. So you can actively change the capacitance just by changing how big or small it is. Okay. Questions so far? We could do a problem where I told you what the area and the distance apart were, and you could tell me the capacitance, right? Yeah, like that would just be a plug and chug problem. So I'm not going to do one like that unless you really need it. Do you need it? Okay.
Wait, Enoch's just a constant, right? Obviously.
Yeah. It's permittivity free space. Yeah. And we'll get to the dielectrics. They're coming, I promise. I've got 2 more pages, and then we're going to get there. We're going to do it today. 2 whole pages. Right here. Here we go. So, as you may know or as you may not know, one of the fun things that you can do when we start to play with circuits is that instead of just putting 1 capacitor in a circuit, you can put multiple capacitors in a circuit. And when you do that, the resultant capacitance changes. So why do you want to do that? Because sometimes you need a certain capacitance for a project, right? For a certain specification. We need a capacitance of 17 farads, 17 picofarads, whatever, right? Maybe you can't go to the store or order online a 17 picofarad capacitor, but you can get, a 15 and a 10 and a 5, right? How can I arrange them so I can get what I need? That's what we're talking about.
4.7 is really common.
No, Wendy?
What's that? We would have to figure it out, right? Yeah, that's what we're going to talk about right now. So we can put capacitors in combination with one another. definitely different ways to put things in combination. We're going to play with this with resistors at lab tonight. So let's just define them. The first one is parallel. To put things in parallel, the easiest way to remember this is that the wires are going to go parallel to one another. I mean, like, it's really pretty straightforward. So a circuit that has two capacitors in parallel will have them branched off like this and both attached to some potential difference. They look very similar, right? You really want to make sure that your potential difference has noticeably different lengths for the two lines so that you know that that's your battery and these guys are your capacitors. Okay? In order to figure out what's going to happen here, we have to think carefully. I'm sorry. You have an eraser, you can draw it bigger. We have to think about what's going to happen here. When I set this up, I've got a potential difference across my battery, right? I'm going to actually call that delta V sub B. As these two capacitors charge, at some point they're going to get to a full charge. What is the potential difference across this capacitor going to be?
Delta V.
Delta V, right? What about this one?
Also delta V.
Also delta V. Is that okay? So I'm going to write this, I'm going to call this capacitor 1 and capacitor 2. And I'm going to say that delta V1 has to be equal to delta V2, and that has to be equal to delta V sub B, the total. So everything is going to have the same potential difference. Tell me about the amount of charge that is stored on this capacitor or on this system versus if there was just one.
It's twice as much.
Assuming
They're
what?
the same.
Assuming they're the same capacitor. We don't know necessarily that they are. So tell me about the amount of charge, total amount of charge stored.
It's C1 plus C2.
Does that make sense to people?
Delta V.
You have to watch out here because AJ's played this game before, so I don't want you to just rely on him. I want to make sure it makes sense in your head as well. The total amount of charge stored here is going to be bigger than if there was just one on there, right? Does that make sense? Okay? The charge here plus the charge here. So the total amount of charge, I'm going to call that Q total, is going to be equal to Q1 plus Q2. Right. So the number, like the amount of positive charge on one, the negative charge on the other. So it's not like adding up the positive charge and the negative charge absolute values. It's the total amount of charge that's separated. You look like you're confused, Teresa.
Because I am.
Talk to me.
I just don't. What?
Ask me a question.
I don't really have a question. I'm just confused. Does that make?
Where did I confuse you?
Okay, so. I'm not even sure about that. Like.
Can we just back up?
Yes.
Okay. So let's back way up. I've just got that.
Yeah.
Okay. So I've got one capacitor and one potential difference. And I really want to make sure this stuff makes sense. So please keep asking questions, okay? If I've got a situation like this, and I set this up and I charge up that capacitor, does it make sense that the potential difference here and the potential difference here will be the same?
Yes.
Okay, good. Does it make sense that in order for there to be a potential difference here, there has to be charge stored, or there has to be charge on each of those plates?
Yes.
Okay. And I'm going to write one more thing down to kind of put all that together. Does it make sense that the charge, the amount of charge that's stored, is related to the potential difference and the capacitance? And we wrote this down before, but we didn't maybe expressly say it. I'm going to write this down right here. That Q is equal to C times delta V. Is that okay?
Yeah.
So C is the capacitance. So the amount of charge is dependent on the capacitance of the capacitor, like
Yes.
the physical characteristics. Is it 7 milliofarads or whatever? And the potential difference of the battery.
Okay.
So far, so good?
Yes.
Okay. So then the next statement that I made was, if I just have this one, I can figure out how much charge is on that capacitor. Life okay?
Yeah.
If I just have that capacitor,
Same thing. Yeah.
same story. If I have both of them in series or in parallel, like hanging out like this, then does it make sense that the total amount of charge stored in this circuit is the amount of charge here and the amount of charge here?
Yeah.
Okay. So that's all I've said so far.
Yeah. No. I think I just got lost when AJ was talking about like it was the capacitance times the because like it was that one thing that you wrote before that I didn't. No, like it made sense once you like wrote down that one thing on the
Okay.
before. Yeah.
Okay. So
Yeah.
life is okay now?
Yeah.
Okay. Cool. So now I'm going to take that thing that I wrote down, Q is equal to C delta V, and I'm just going to write it down here. So instead of writing Q, I'm going to write this as the C, and I'm not going to write C total because usually we call it equivalent. So I'm going to call this CEQ. Means equivalent. Equivalent. What is it? Okay, I don't spell well. Level 3 speller. Right here.
Check that on the AP test.
What's that?
Check that on the AP.
I think if they can figure out what you meant, it's okay. Yeah. Equivalent capacitance. So that means what one capacitor could I replace these two with in order to make the same situation? So CEQ delta V total, that's like the battery, is equal to C1 delta V1 plus C2 delta V2. Is that statement okay? So all I've done is to sub in, instead of for Q, I have C times V. But then somebody says, but wait, who's going to say that?
The V is the V1, V2 are the same as VB.
So we can divide by V what?
B.
We could divide by V, right? That's what I'm trying to say. So you can say that the equivalent resistance is equal to, or excuse me, equivalent capacitance, I'm getting ahead of myself, is equal to capacitance of 1 plus the capacitance of 2. Is that okay? This is a big deal. You may want to write down parallel capacitors. So, then I could give you a problem and tell you that the capacitance of C1 is 7 microfarads, and the capacitance of C2 is 3 microfarads, and you tell me that the equivalent capacitance is? There, that was fun. Life is okay?
That's how you get a 5 on the AP test.
That is how you get a 5 on the AP test.
That's all it takes.
Except now we're going to also add the other kind of combination process, which would be series. So let's put them in series.
Perpendicular.
Good guess, but no. If they're in series, that means that it's all one loop. That's the game. This one's a little bit different here.
I like this one.
I think it's kind of cool, actually. Not trying to be, not even snarky, but, like
Contrarian.
contrarian, yes. Okay. So I've got two capacitors in parallel, or excuse me, in series. Try and speak correctly. Two capacitors in series. They are not yet hooked up to the battery. Right now, I have a question. For the series capacitors, this is the thing we have to keep in mind. I'm going to put a box around this stuff here because this is electrically separated from everything else, right? There's no wire connecting these. There's no wire connecting these. Are you with me there? What is the net charge inside this little dotted line? 0. Okay? When we're using capacitors in a circuit, will there be any charge flow across the capacitor, across the gap? No. So what is the net charge going to be here the whole time? 0. Does that mean that we can't separate charges? No, we can separate them, but they're always going to have a net charge of 0 around this, or in that box. Is that okay with everybody? Okay. So, now we're going to shut the switch. I'm going to make it a little bit bigger. Kind of to make Jack mad and also just so that I can point things out better. Sorry. Abby's like, I can do that.
Yeah.
I love it. Now I shut this. So now the potential difference that is across here, delta V sub B, okay, is causing a potential difference. Well, it's causing an electric field to cause charges to move. Would you agree? Okay. Now, what's going to happen? What's going to happen as those things charge up?
The potential difference over the whole thing is delta V sub B.
The potential difference from this point way up here to this point way down here is going to be delta V sub B. It's not going to be the same here and here this time. Does this make sense to you? Is that okay? The potential difference is going to be, of delta V sub B is going to be the same here and across the whole thing. Which means that if I look across each small piece, like here and here, let me label this stuff here real quick. I'm going to call this C1 and this one C2. And I'm going to call this delta V1 and I'm going to call this one delta V2. What do you know about delta V1 and delta V2? The potential across this capacitor.
They have to add to.
They have to add up to the total voltage. Is that okay? Okay. So delta VB equals delta V1 plus delta V2. So far, so good? Okay. Now, thinking about charges. What's the net charge inside this gray box again? 0. So any negative charge that collects up here will have the same positive charge that collects right there. Does that make sense? And any positive charge that collects here is going to cause the same negative charge to collect here. Does that make sense?
But there's no electric.
And up here as well. What's that?
There's no electric field created between the. Yes.
In this space?
Yeah.
There is,
Okay.
because you've got a separation of charges.
Okay.
Does that make sense?
Sure. Yes.
You just sound like you're trying to convince me.
No, I get it.
Are you really okay with that?
Yeah.
Okay. So the charge, like the charge stored in this capacitor and the charge stored in this capacitor, how do those compare?
Equal.
He says equal. Does that make sense to you?
No, because they could be different.
Yeah.
Say what now?
They could be different.
Why?
So,
How?
like difference in area and
There's the charges that you bring the one in the middle.
How much charge do we have to have in this box though?
0 net.
0 net charge. So any positive charge, excuse me, any negative charges that collect here, you're going to be left with the same amount of positive down here. Is that okay?
Yeah.
Yeah? Are you sure? You guys don't look completely convinced. So I can't quite tell. This is what we're saying. The total Q is going to be equal to the same thing as Q1 and Q2. We have similar things written down, but it's not the same thing. They're actually opposites of one another.
So Mike, I wonder, so I have a whole bunch of wires and I have 2 capacitors. All this stuff is different depending on where the capacitor is.
How they're arranged with respect to one another. I think, am I understanding what you're asking? Say that again.
Okay.
Say what you said one more time.
I think I get it now. They're both in the same series instead of it being, okay, I get it. Instead of it being another wire that goes to another capacitor, they're both capacitors on the same wire.
they're on the same path.
I got it.
Nathan?
What are you defining as Q1 and Q2?
Q1 is the charge stored in this capacitor,
Okay.
and Q2 is the charge stored here. And the charge, it's the positive charge here, it's the negative charge here. The same, it's the value, the magnitude.
Q1 and Q2 the same?
They have to be the same.
Are they the same as Q total?
Yes.
How is that possible?
Are you
The opposite, yeah. Because if the middle part's 0, then all the positive charge is on.
When we talk about the charge stored, we're just talking about a magnitude,
Okay.
right? So this plate has positive charge. This plate has negative charge.
Yeah.
This plate has positive charge. This plate has negative charge.
Yeah.
The positive and negative here will always be equal by definition because of the capacitor. If they're in series, the amount here and the amount here must be the same. Is that okay with you?
But Q total is Q1 is equal to Q1 and Q2. It's not because
So what I'm saying, okay, let me back up for what I'm saying about total. I'm going to go back to the other one for just a second. What I mean by total is if I was going to replace this capacitor, or these capacitors, with one capacitor, how much charge would I store? Okay? So here, if I'm going to store charge on one capacitor that looks like these two put together, that I wouldn't even know, right? It's a box.
Okay, so you just, like that wouldn't matter, you could just do the same thing with one capacitor then for the bottom one.
Say that one more time. I just don't know if I'm understanding you.
Well, based on what you said then, if you place the two capacitors and make just one equivalent capacitor, then that would have the same thing.
The same charge stored. Yes. Is that okay?
Sure.
So the game is, and maybe I wasn't articulate about this enough. The game is that, let's say that these capacitors are sitting in a box. What I want to be able to do is take these two capacitors out, replace them with one, and from over here, making any measurements you could make, you would have no idea that I replaced them with one. Okay? What I want to do when they're in series is to take these two capacitors and I'm going to put them in a box. So you set up this circuit. You had two capacitors. I came along, snuck up, opened your box, took the two capacitors out, put one in and locked it back up. You come up and you make measurements over here. You have no idea that instead of the two capacitors you had set up, I've just put one in. That's what I'm trying to do. Does that make a little more sense?
Yeah, at first I thought you were like the total charge of the entire thing is equal like the charge of both capacitors.
Yeah, right. So does that distinction, that helps a little bit? Okay, yeah. So that's my fault as well. Yeah, so the total charge, it's like the equivalent charge that's being stored on both of them together. Okay. So now I'm going to, what's that?
call it Q, EQ?
You could have. And I was just thinking that we just don't usually call it that.
So
That's not,
Q,
yeah.
QT isn't like the Q, like for the biggest green bracket. It's not that Q.
Just talking about
Well, hold on though.
just saying.
Let's back ourselves up for a second.
Saying if you replace
If I have,
the two capacitors with just one capacitor, then have the potential.
if I have a capacitor, and you're looking at the charge on the capacitor, right? You're just looking at how much positive charge there is. We count up all the charges. It's got 0.3 microcoulombs of charge. Okay? Now, if I have two capacitors that are in series, and this one, what did I say, 0.3 microcoulombs? Is that what I said before?
Yeah.
This has 0.3 microcoulombs of negative, right? This is positive 0.3. This is negative, and that's positive. That is the total charge that is on those capacitors. I think you're just getting a little unhappy about that because it's not adding, right? You see what I'm saying? Does that distinction make sense? Nathan?
Well, I'm trying to figure out how this works now. So say you place a third capacitor in the middle.
In between them?
Yeah.
Okay, we can do that.
Well, then you would have.
Yeah.
I'm listening.
Now I just see it's weird.
There are two areas where there's no charge.
That's what I understand.
And all three of the capacitors.
That's what I'm saying.
Okay.
Nathan, I want to make sure I'm understanding what you're saying. Is this the picture you're talking about here? Down here?
Yeah.
Okay, so if we have, just going to make it bigger so it's easier to see. So we've got 3 capacitors. We've got C1, we've got C2, and we've got C3. Everybody good? Okay. The net charge on this plate, the wire in the plate, is 0. This plate, the wire in the plate, is 0. But this is a capacitor. Is everybody okay with that? Okay. So let's talk about what physically is happening here. If I connect this to a potential difference, there's a positive terminal of that battery, right? And not another positive. Hello. And a negative. Okay? So positive charge is going to follow the electric field this way. Are you with me here? Okay? And it's going to collect a bunch of positive charge here. Everybody happy? Let's talk about this. Now, does it happen this slowly? No, but let's just kind of work it through. If you've got a bunch of positive charge here,
This is going to cause a chain reaction.
yes, that is going to cause any positive charge that was hanging out right here to be pushed down and leave negative charge there. Are you with me? So there's a bunch of negative charge here. And the charge that lives right here and the charge that lives right here, it's the same amount of charge. And we've got a bunch of positive charge that is here because there was an electric field going like this, right? That causes this separation of charge right here. And so now I've got a bunch of positive charge here, and by induction again, what's going to happen here? Same thing that just happened again. So you're going to get a bunch of negative charge, choop, 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 okay? And then you're going to get a bunch of positive, you see what I'm saying? And negative, and the amount of positive charge that's hanging out here and the amount of negative charge that's hanging out here will be the same. If I put 17 capacitors in series with one another,
Do that.
I'll let you do that as an exercise for yourself. I don't want to have to draw that. But it's the same deal. You see what I'm saying?
Wait, so then why isn't total capacitance just the same as?
We haven't gotten there yet. We need to finish it.
Oh.
Because the voltages aren't the same. The voltage across this whole thing is this voltage.
Right.
So this little voltage and this little voltage and this little voltage have to add up together. So let's do that and let's see what's going to happen. Let's do that process.
So in this
But-
one,
Well, just hold on. Just
hang on, no, in the last one, charge added and voltage was constant.
right. That's what we're doing.
In this one,
It's flipped.
uh,
That's why it does what it does.
No, wait.
Whoa! We learned something today from AJ. Yay! Nathan, are you happy back there? Are you happy?
They all seem very golf back there with all their.
I know, right? I was thinking that. But we need to keep going. So tell me, are you okay? Does that answer the question you were asking? Okay. All right.
Gabe's joining in.
Here we go. Guys, stay with me. We don't have a lot of time. Thank you. All right. So Teresa's favorite equation is that Q equals C delta V, right? I'm going to change. I'm just going to solve that for V. So delta V equals Q over C. And I'm going to take that expression and take this addition and put them together. And this will answer AJ's question. So, instead of delta V sub B, I'm going to write, I want more colors, we'll do blue. Q equivalent or Q total divided by C equivalent is equal to Q1 over C1 plus Q2 over C2. Is that okay? Then Brian says, what do you say, Brian?
Say that looks about good.
No, that's not the end.
Since all those are equal, we'll have just 1 over C equals C1 plus C2, which looks familiar.
Well, you have to be really careful though. I'll write it in blue so that we're staying consistent here.
Half the harmonic mean of the two.
Yes. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Okay, it does. Now, you've learned this. You learned this a long time ago. This was preschool time for Logan back there. This does not mean that if you have 1 over 3 and 1 over 2 that it's 1 over 5, right? We know the rules of fractions. You don't just add denominators.
Sure. You subtract.
You need to know what you do. What do you do, Peyton?
I think you said it wrong.
Divide.
Sorry, you got it.
Common denominators, friends.
Okay.
Okay,
Well, maybe you can.
so I'm going to throw a problem up here for you to work on. This one is putting things together. The picture is not great. The question asks for you to find the charge and potential difference across each of the 3 capacitors, but first you need to find the equivalent capacitance. What? So let's take a look at what's going on here. You've got your battery over here. Remember I told you they didn't actually draw batteries the right way yet. So you've got your battery. It's 12 volts. This is not too hard. You can do this if you stop whining.
What example is this? 29.7.
29.7.
Okay.
It's not sending.
29.7 in your book. Okay?
It's steadfast.
I want you to find first the equivalent capacitance. Do that right now. Talk to your table mates about how you might do that. Because this is a little bit more complicated, right?
Batteries and
What do you have going on?
Some guy really wanted to make people mad. Yeah.
2 steps.
Okay, so it's 6. Then 1 6 plus 1 third is 1 half. So the answer is 2.
parallel you add
I disagree.
in series. The reciprocal of the total is the sum of the reciprocals.
Not 2. So what do you want us to find first?
The equivalent capacitance.
Okay, so
Why don't you go type it in?
Are we okay with the equivalent capacitance part?
Wow, yeah.
I mean, I was drawing it.
Oh, okay, go ahead. Keep going then.
So the picture's good.
Good.
Okay, so what's the equivalent? 6 microfarads.
yes.
Right? And then you have 3 microfarads and 6 microfarads. So 1/3 plus 1/6 is 1/2. And that's the reciprocal of the total capacitance.
Oh yeah. Oh, okay. Oh.
Is that okay?
Yeah.
What'd you guys do? Yeah.
Let me
Oh,
know.
that'd be kinda cool like that.
That's not too bad, right?
Once
Okay, so
you like everything. It's not that bad once you get it.
what is the equivalent capacitance?
Too much.
Okay. Now, the question actually asks for you to find the charge on and the potential difference across each of the 3 capacitors.
Be smart enough.
How you are smart enough. What are you going to do?
Well,
We know that potential difference. Use series. Find what the 2 should be in each second one to find a parallel. Nailed it. Q equals.
you got the
Oh yeah, but I guess you need to find it.
and Q total
Q total will be the charge on this capacitor, right?
and on the bottom one.
And on
The
some
parallel.
combination of these, right? But we don't know exactly how much is going to be distributed where.
Yeah.
But on
But-
the sum.
If you know the equivalent capacitance is 2, then you can find the charge that's stored because you know the voltage. Are you with me there? So 24. So it's coming back. So the charge stored, 2 microfarads times 12 volts is going to be 24 microcoulombs of charge. 24 microcoulombs of charge is stored on Q1.
I just realized we never really defined a farad. We never really said that a farad was a coulomb per volt, right?
We kind of said it,
You
but
just
you weren't
did.
paying attention. But
Then
yeah.
we know, since we know that.
Now that you know Q1, can you figure out what the voltage is across this one?
Yeah, that's not right.
Because you know the capacitance of this one is 3 microfarads, and you know the charge is 24, so what's the potential difference across this one? 8? Does that make sense?
Okay.
Yep. So delta V for 1 is going to be equal to Q1 over C1, so that's 24 microcoulombs divided by 3 microfarads gives you 8 volts. So that's 8 volts of potential across this one, which means how much potential difference is there across this part? 4. So this has a voltage of 8, so that means this one has to have a voltage of 4. If you know that has a voltage of 4, so delta V for 2 equals 4 volts. And you know C for 2 is 5 microfarads. So Q for number 2 is going to be 5 microfarads times 4 volts gives you 20 microcoulombs. And then, one way or another, there are 2 lovely ways to figure out how much charge is here. What's the easy, fast one?
Divide that by, wait, no, do the same thing. 1 times.
You could do the same thing. You could also, how much charge is on this one?
Oh, yeah.
24. 20 of them are over here. How much has to be left here?
4.
Okay. We doing all right?
Wait, why?
Because in series the charge is on all the capacitors. in
So
series.
these charges and these charges.
Oh, yeah,
are
yeah,
together.
yeah.
Yep.
Oh, okay, yeah.
And then
All right.
Um,
I think it's time for you to leave me.
I gotta have a question. Like,
Yeah,
I
go ahead.
understand everything like of how it went afterwards, but I don't understand why you were able to use the 12 volts on the first
Here?
Yeah.
So this was the equivalent. And equivalent. Because, so that's like if this thing was all 1, it has a capacitance of 2 microfarads. Is that okay, that statement? And the charge on this plate is going to be the same whether it's 1 capacitor or a whole series or a whole combination.
Because of the series.
Because of the series stuff.
God.
Exactly. Does that make more sense?
Yeah.
Yeah.
Carbling, I asked a question. Why did they draw that